We need to talk about as many characteristics of higher degree polynomials as possible. Why are we trying to figure out as much of this as we can? Because why? Okay, good. I mean, the green circle says we want to be able to graph it by hand. Now, I already told you, like for this one, you're only going to be able to do so much. Because what do you have to learn to be able to get that graph precisely? Calculus. Eileen, from Calc AB, would you guys eventually have been able to graph that entire function using the 14 identifies? Yes. Once you get through first semester Calc AB, you can find that entire graph. All the little maximums and minimums and the different branches and the intercepts and all that jazz. Without calculus, we can only do so much, so we need to talk about as many characteristics as possible to try to figure out as much as is possible of what's going on. What were we talking about yesterday? We basically focused on one big idea. And what was that one big idea? The end behavior. For even and odd degreed functions. And did we talk about a cool note? Not a cool notation. To me it's cool, to you it's like whatever, it's an arrow. But did we talk about new notation? And the answer is yes. Eileen, is the arrow important in calculus? What does it mean? Oh, sorry, this arrow.
Oh, that arrow, approaching.
Yeah. Approaching, super important in Calculus 1, Calculus 2, Calculus 3, and beyond. It's actually what makes all the calculus possible, with huge implications and applications in biology, in economics, in finance in general, in business, in physics. Anyway, this little arrow, super important. So we talked about what this means. As you're going, well, you guys tell me. That's no fun. All the answers are there. What's this one mean? As x approaches negative infinity, how would you explain that if you were tutoring someone, what this is talking about? Yeah, as you go towards the left. You can say the left side. The problem is this arrow keeps on going. So I say to the left because we can't actually see the far end of the left. Does that make sense? Because the left keeps going. So as we go to the left, right, x to the left. So x going to positive infinity is as we move to the right. And what are we moving to the left on? What are we moving to the right on? The axis? No. What are we moving on? What's this guy called? The formula? I'd say the function. That'd probably be the best way of saying it. But the function? So we're moving on the function, and as we go to the left, as x approaches negative infinity, where are the y's, or where is the function going? Negative infinity. And as we go to positive infinity, as we move on the function to the right, where's the function going? Positive infinity. What happens when the leading coefficient is negative? Everything switches. So we talked about end behavior yesterday. You guys, I don't think, need to write this down, but do you understand why they show dotted, 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 dotted in between? What are they trying to show you? When n is odd, regardless of, what's this dotted stuff showing you? Yeah, it's an example of a function, but why is it dotted? What are they trying to show you? Try to think in the publisher's mind for a second. Why is it dotted? If all they have said is n is odd, leading coefficient is positive, why is that dotted? It doesn't matter what's going on. It could be one of these, it could be one of these, it could be one of these. It doesn't matter what's going on. As long as n is odd, the leading coefficient is positive. Coming back. As n is positive, as leading coefficient is positive and n is odd, it doesn't matter what's going on in here. All that matters for end behavior is what's going on in the ends. As I go to the left, as I go to the right, that will always be true. If the leading coefficient is negative, it doesn't matter what craziness is going on. As I go to the left and as I go to the right, those are true. So, I want you guys to go ahead. Oh, wait, okay, even. Ready? Set. Show me the ends. I don't care about the middle. Show me the ends. Actually, don't show me. Describe to me the ends of each of these. As x goes to negative infinity, so you know where the video is online. Check it out. Homework is on Monday. describe to me the behavior of f, regardless of what's going on in between. There is no solving. There is no factoring. It's looking at the function and telling me what f of x is. Does it make sense what I'm asking? Ready, set, f of x approaches, you guys fill in the table. Okay, 30 more seconds. All right, go ahead and check in your groups, kiddos. Do we all agree?
Positive or negative, y approaches and then his x approaches
I thought it looked like this one. I mean, I'll take this address.
Oh, sorry,
Sorry guys, that's next. Okay. Group number 1, 2, 3. What do you guys say for the first one? F of x is approaching? Group number 3, pause. What do you guys say? Dr. Thomas or Angie? Positive, then. And as I go to the right, F of x is approaching? Let's check it. Oh. What do you guys think? Are they right?
No.
Pause. As x approaches negative infinity means as you move to the left, to the outer ends of the left, are the y's going up? Yeah. To the left and up, they got it. To the left, up. As x goes to positive infinity, as I go to the right, the function needs to be going down. Good. Odd functions. Positive leading coefficient, negative leading coefficient. It's as easy as that, right? Even functions. Positive coefficient, negative coefficient. It's as easy as that. Right?
Yeah.
Just throw in here a couple of answers and you guys should be good. So how about the second function, group number 1, 2, 3, 4, 5, 6? What do you guys think?
For both of them, it's x approaches infinity. F of x approaches infinity.
F of x approaches positive infinity. Let's see if they're right. As I move to the left and to the right, are the y's going up?
Yes.
Regardless of what's going on in between. Final function, group number 1. You guys think approaches negative infinity and then so negative infinity on top, positive infinity on bottom. Huh, interesting. It's opposite or switch the first function. Would that make sense according to what you see? Leading coefficient is opposite. It's still an odd degree. Let's see if they're right. As I move to the left, is it going down? And as I move to the right, is it going up? Does the notation make sense? Questions on the notation? F of x represents what? Function or y values. Okay. Function values or y values. And we already know that x represents horizontal or x values. Okay, let's keep going. Good job, guys. Ooh. Why do we not start talking about zeros? So far, my little arrow is not showing up. So far, what have we only talked about, realistically? And behavior. But the problem is, if we're getting close to graphing, how could we have found out more information than just the ends by finding the intercepts? If we can find intercepts, do we at least have an idea of what's going on? Maybe not perfectly, but an idea. If we have intercepts, we have an idea of what's going on. Because, for instance, if this one right here only had one intercept, and we know it's going down to the left and up to the right, if it only had one intercept, what would it look like? Probably like this, right? Probably like this. That would only have one intercept, right? That hits right here in the middle. Or it could have been this, but shifted down, so it only hit once. Maybe the intercepts don't tell us everything, but they do tell us a lot, so it's time to find zeros. The struggle is finding zeros. We'll get into factoring. I'm going to take out or use the quadratic formula. That might be a tool that we use. Completing the square might be a tool that we use. It depends. Also, I'm going to put in parentheses. That's a little better. I'll put that instead. Grouping sometimes works. For cubics, rarely. Sometimes it works. But before we even talk about finding zeros, remember, those can get really hard for cubics. They can get hard for quadratics, but cubics, we don't have a cubic formula. All we have is a quadratic formula. Quadratic formula comes from complete the square. We don't have a complete the cube, sadly. So we're going to talk about what you guys wrote first are the clues, just to give us an idea of how many we're looking for. You guys remember what n stands for from the beginning of those? What's n of a polynomial? Nth degree, okay. Remember the degree is the highest exponent, true? Quadratic degree 2, cubic degree 3. At most, polynomial is going to have the same number of real zeros as its degree, at most. Which means you can have 0, 1, 2, all the way up to whatever the degree is of the function. So it doesn't tell us exactly how many, it just tells us at most. And along with that, one more clue, it could also have n minus 1 turning points. So for a cubic function, what's my degree, guys? 3. So it could have up to 3 branches. It can have up to 3 zeros. It can have up to 2 turning points. Does that make sense? What's a turning point? A max or a min? So a cubic, does it have to have any turning points? No. But if it did have a turning point, if it has one, what else must it have? Another one, because it has to start. If it stops from increasing or decrease for a little bit, it has to change again because it has to end at increasing. So either a cubic, technically, is going to have no turning points or 2 turning points. There is no in between. How many turning points will a quadratic have? 1. Because a quadratic, well, has to change direction once. It has to start from up and then end at up, or start from down and end at down. So a quadratic, n equals 2, has to have 1 turning point. A cubic, n equals 3, has to have either 0 or 2 turning points. You guys make up a degree. Do you want to do 4? Do you want to do 5? Do you want to do 9? Do you want to do 11? Not 3, 7. Keep it below 10. Pick one. 9. Okay. Is it going to be a positive leading coefficient or a negative leading coefficient? Negative? Alright, so it's going to start from decreasing, or it's going to be increasing to the left. It's going to end decreasing, or it's going to be decreasing to the right. According to this, how many zeros could a 9 have? 9. How many turning points could it have? 8. Could it have 8? Yes. I can have 1 branch, 2 branches, 3 branches, 4 branches, 5 branches, 6 branches, 7 branches, 8 branches, 9 branches. Okay, how many turning points is that? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I shouldn't say 8, but I have, these will be my turning points. Question. This one has 8. Could a 9th degree have 5?
Yeah.
Okay, so then we have to start, you guys said negative leading coefficient. How would it have 5? There's 1, there's 2, there's 3, there's 4, there's 5. Count it. Do I have it right? There's 1, there's 2, there's 3, there's 4, struggle. There's 5. Could it just have 5? Because how would my function need to end if it only had 5? That's not a 9th degree. How come? It has to start and end oppositely, right? So question. It can't have 5. What can it have? 6. What does this tell us about turning points? For odd degrees, it's going to have an even number of turning points, whatever it is. The maximum is 1 less than the odd. So it could have 8, it could have 6, it could have 4, or 2, or 0. For an even function, do you think it's going to be the same thing? It's going to be an odd, but it could be any odd. So if you had a 4th degree, how many turning points does it have? 3 or 1. Does that make sense? Has to be every other in order to make the end behaviors end correctly. And then finding zeros on something to do with factors. Uh-oh, let's keep going. Where is this going to lead us? Oh, whew. Man, that's an easy one. That was close. How do you find all the real zeros? Yeah, this one's a nice one, right? Nothing too crazy. So all we're going to do is take out the common factors, setting the whole thing equal to 0, or the common factors. Why are we going to pull out the negatives to make it nicer? It's nicer to have a positive first term of a factor, in my experience. So what's left is for the first term? X squared, and what's left in the second term?
Plus,
2. So we take away the 2, we take away the x squared. Because of the negative, we have to make sure negative times a negative is a positive. So I have to make sure it's a minus. One quick thing that a lot of people tend to confuse. When I pull away the 2x squared, when I factor the 2x squared, a 0 does not remain. A 1 does. Some of you, it's just so natural you don't even think about it. And you put the 1. But for other people, it's just as natural to have a 0. Can anyone tell me why 0 would be incorrect? You have to be able, good. She said you have to be able to distribute. You have to be able to distribute and get each of the terms. That's one way. The second way is whenever you factor, distributing you're multiplying, factoring you're dividing. So if you divide 2x squared by negative 2x squared, 2x squared over negative 2x squared is a 1. Whenever you have a number over a number, it reduces to be 1. That's why I call this reducing. Reducing to be 1. This cancels to be 0. Right? How do we keep going? Can we factor anyone? It's a quadratic. Come on, cool kids. We don't have to factor quadratics. What's x squared minus 1 factored?
X plus 1 minus 1.
How many real zeros does this one have? Why 3? I need this one, negative 1, this one, positive 1, which I just shortcut plus minus 1 because I'm lazy. Set this equal to 0, which will be when x equals 0. There are 3 zeros. How many zeros total could it have had? 4. But I only have 3. How is that possible? Kiddos, I know that a 4th degree, well hold on, don't you know that this guy has ends like this? Is it possible with 3 different zeros that this is just a parabola? Because what's the maximum number of zeros this guy's going to have? Okay, so what must be going on somewhere in between? It must be having some turning points. Now the maximum number of turning points is 3. Let's see if that's the actual, and remember it could be 3 or 1 if we were just talking about turning points. The maximum would be 3, it could have 3 or 1. We just tried 1. Would this one make more sense? But the problem is, how many zeros could this one have? Well then how can it only have 3? Calm down, we're good. Let's sketch it. So we have 0 plus or minus 1. I'm just going to give away. Can I just give it away? Roughly. Isn't that 3? Here's my negative 1. Here's my positive 1. Here's my 0. 1 and a 2 and a 3. How did I know that? Because I learned something called multiplicity. And multiplicity says if there's a 0 that technically is shared, only this one has a multiplicity of 2, and what that means is there was actually an x and another x, and both of their zeros were 0. Both of them shared the same 0. Both branches met at the same 0. Whenever you have a multiplicity of 2 for a polynomial, it's always going to bounce out. It's always going to skim the axis. It's always going to cross through and come down into and up over, or come up to and go right back down at. Repeated zeros. You guys get it done? When factors are raised to a power k, it has a multiplicity. Whatever that multiplicity is, I should have said this, even. The graph is going to bounce. Don't worry, I have that in the notes. We'll write it down. But do you think that could be a helpful clue to helping us visualize the graph of this puppy? Visualize the graph of this polynomial. Now, do I know exactly how high this goes? No. Not right now, not just with what we've done, but I do know that it goes down to the left, it goes down to the right, it comes up through -1, has to come back down at a turning point, bounce at 0, come back up turning point, and go back down through 1. That's a lot of information to figure out just from factoring and end behavior. Repeated zeros. If you have some sort of x raised to a power or any factor raised to a power, we can say that they are repeated factors. So this x was repeated. He had a multiplicity of 2 because the x was being squared. These ones technically have a multiplicity of 1, but is 1 really a multiplicity? Multiple? No. 1's just 1. Leave it at that. Let's get this clue next, because I was just talking about it. Let's get this clue next. We're talking about multiplicity, and since I had you write it down, let me go ahead and have you do this next. We do have this thing called multiplicity. If we do have factors, see, it's going again, Colby, but now you're falling asleep. You doing it right then? Colby. It's warm. You not feeling good? Come down. You not feeling good? Hang in there, it's Friday. I know, it shouldn't be this one. Alright, we're awake. See, warm is good, but then it's not so good. Struggle.
We need to solve the temperature 70 to
I think it's set right now at like 73. But it takes it too long to kick in, so it's already gone from 73 to like 77. And then when it gets cold, instead of stopping at 72, it keeps going to like 70. I don't know, it just did. Oh no, it's not. It's not 77. It's like 74. Okay, so it's not too bad. I read my thermometer wrong. Getting my coffee. Help Colby wake up. You're welcome, Colby. Okay. So we just had an odd multiplicity, and what happened? It bounced off, right? But even, I am trying to remember what should go in this quote, and I do not remember. No idea. There's some way of remembering it. Yeah, but then I put bounce. See what I mean? Huh. I was going to say bounce off and cross through, and like that's exactly what the blue says. So, I'll think of it. If I can think of the way of remembering it that I've used in the past, I'll try to come back to it. Wow, it's not in my head at all. Cross through and bounce off, that's all I got, but that's kind of lame because that's what the blue says. Anyway, if you have an odd multiplicity, and it doesn't just have to be x, it could be x minus 2. That's squared, that's cubed. Whatever that 0 is, wherever that 0 is, either odd multiplicity will cross through or even multiplicity will bounce off. But wait. Didn't we just say kind of that we could say these guys have an odd multiplicity? It's not very accurate if you think about multiplicity meaning multiple. But couldn't this be, I know, weird, multiplicity of 1? That's an odd multiplicity, and what happened at negative 1 and 1? Cross through. So it technically even works even if you're thinking about a multiplicity of 1. Kiddos, pause just a second. Just put your pencils down. I don't even want you to write this page. Because I think with all the other clues that we've talked about, we will be okay to skip this. But it is kind of good for calculus to think about this idea of a sign chart. We just talked about how we have negative 1 and 0 and 1. Think about this as the x-axis, the horizontal number line, x-axis. We have those as our zeros, true? We also know that as an even function with a leading coefficient negative, we knew it had to go down and we knew it had to go down. In your brains, did it make sense to you that this has to come up through and then back down to and then bounce off, back down through? Does that make sense? Okay, so I think the clues that we have are good enough, but technically there is another way of thinking this through if that's not very logical for you. What you could do, and this actually will probably help in the long run, ultimately the sign chart idea is just saying, hey, we don't know exactly what's going on in between -1 and 0, even though we do know it has to come up through. We don't exactly know what's going on in between -1 and this downward arrow. We don't know exactly what's going on between 0 or 1, or sorry, between 0 and 1, or between 1 and this little downwards arrow. For instance, this downwards arrow could be way over here, right? Be kind of awkward, but it could be way over here, and we don't know. So the idea is, with the sign chart, because we don't know calculus, and sorry, it's true, we don't know calculus. And I can't teach it to you today. It takes me a semester with AP kids. We have tons of honors classes, it might take me half a semester, but either way. We basically have to say, what's going on at -2, what's going on at -1/2, what's going on at 1/2, what's going on at 2. What are we doing? We're taking a quick little peek into each of those intervals and saying, I need some sort of point to be able to connect my stuff. And hopefully it'll be as close as I can get without knowing calculus. Now, how do we actually plug into this? Go to the table. Sorry, go to the table. Go to the function. And so the function, I'm going to show you guys this in the next one. Here's where I want you guys to go ahead and come. All right? We've already done a lot of the work for this problem. So we already know that this function can be rewritten as -2x squared, x plus 1, x minus 1. If the directions were to sketch the graph, they say sketch, you're not using your graphing calculator, you're going by hand in this section. You're going to go ahead and say, mark the 0, mark the -1, mark the 1. In a sense, you're working out your intervals. You're saying, okay, something's going on from -infinity to -1. Something's going on from -1 to 0. Something's going on from 0 to 1. Something's going on from 1 to infinity. How do we get a peek into that table? And we can put a little arrow and say, we know eventually what's going on. But to actually get the best sketch possible with the level of math that we know, we have to make a table. And so I'm going to go ahead and get my x and f of x. You can make it horizontal or vertical, whichever one's easier with how you're doing your problem. But use these intervals. Use what's outside each of these or in between each of these zeros and say, I need to know something. Does this go way up to like 10 or does it go up to like 1/2? That's a big difference. We just need to get a peek to do the best we can. Once again, it might not always be precise, but it's the best we can do. Do you guys see why I'm choosing -2, 1/2? Sorry, -1/2, positive 1/2, and 2.
Yeah.
Could I have chosen 5, -5 and 5, or -1/4 and 1/4? I guess. I just have to choose something. When we plug in -2, mental math, help us out. Would it be easier to plug in here and have to do the 4th degree, the squared degree, and move stuff together, or is it easier to do plug in, multiply? I think this is easier. For some of you, if you're really good at mental math, maybe that's easier. But as they get long and complicated, it's usually easier to plug into the factored if you can. So for instance, plugging in -2 here, I would have -2 times -2 squared is 4. -2 plus 1, -1. -2 minus 1, -3. And what do I have? -8, positive 8, -24. Whew, well, that went down really fast. I mean, I guess we could have plugged in -1.5, but that doesn't sound very fun. If I plug in -1/2, oh, this is going to be awful. Pause. -2 times. What's -1/2 times -1/2? 1/4. No big deal. What's -1/2 plus 1? 1/2. What's -1/2 minus 1? -3 halves? -1.5? -3 What am I going to have? Well, you can cancel out one of those two. So we end up with -3/8. Positive 3/8. That didn't go very high. It's kind of important to know. The nice thing is, if you guys notice, if I plug in 1/2, since the function has even symmetry, plug in a -x, everything stays the same. What would happen if I plugged in? That one's going to be 3/8, and this one's going to be -24. Sometimes symmetry saves us an awful lot of work. And we can end up then being able to say, hey, at 0, I know he's there. At -1, he's there. At -2, oh dear. At 1, he's there. At 2, he's there. If I make this 1 and that's a half, then 3/8, well, doesn't go very high. Doesn't go very high. At maybe a half and a half. And what's going on at 2? I don't know, but he's low. What's going on at, sorry, that was -2. At +2? Don't know why I marked 0. That's random. End of the day. Kiddos, go ahead and grab them. Let's see how close we got. If only I could do that so much. Grab them. How close do we get? See if I missed anything. I plugged in some points and I hope that that's kind of what's going on. The symmetry kind of helped me. I'm pretty sure the maxes are at -1/2 and 1/2, which is halfway in between. Because I see the symmetry. It's not always true. There's not symmetry, I'm in trouble. I have at least 3 people checking, which is good. 4 people checking, which is good. Once you have it on your calculator, hold it out. There's a lot of people who aren't looking. Show them. Show your group. How'd I do? Not too shabby.
-2 versus +2. Are you sure?
Because if I plug in a +2 squared, it's still 4. 2 plus 1 would be +3. 2 minus 1 would be +1, but this ends up being a positive anyway. So that would be a positive times 4 times a negative, it will be -20. But you're right, it kind of changes, but it ends up the same. Alright, so I didn't do too badly?
No.
Alright, ready, set, go. Do everything. Ready, set, go. Do everything. Without your calculator, put that calculator down. You can check it after you do all the work. Follow what I did.
Are we allowed to work with that group?
Sure. I don't mind that.
Good question.
Guys, long story short, don't get stressed by the A and B and C and D. Everything that I just did answers all those questions. I don't even care if you don't even really write A, B, C, and D. Just get to the graph. Think about the ends. Find the zeros by factoring. Make a little table, put it all together, and see how close you get. Ready, set, and go. I bought it. It was like in a little thing of puzzles. Ryan's gone still for his baseball. Sorry, other than who else is gone? Oh, Toby left, but he was here to be at the beginning.
There's Toby.
You guys ready for me to start playing? I won't mess you up if I just go.
Give me a second.
Oh.
First one, wait. So do you do numbers? Three. -6 and -3. There's one outside and then 2 times. It's good.
How are you guys plugging in? You plugging into the beginning or to the factor one? Isn't it easier? I don't know. Do you guys do what, -6? Ooh, do you do -5 halves and 5 halves?
Yeah, that's what I'm.
That'd be cool if you did. Some of you are a little lazy and picked -2 or -3. You have a rough sketch. You just be a little off. Just a little. Well, you -6. What'd you guys get?
We didn't do that.
We're doing negative
-66, right? Okay. Is there symmetry? Is this one 66?
Yeah.
Yeah. Cool. That's nice. But it's opposite, right? Because we know that one's going down and one's going up. These are zeros. Yes. -6 is like way down. +6 is, holy cow, way up. -5 halves. That would have been -5 halves. +5 would have been +5 halves. -5 would have been, you guys know how to do like fraction with whole number quickly, mental math style, right? The common denominator, so 5 times 2 over 2 is 10 halves, so -5 halves minus 10 halves would be -15 halves. Anyway, it's more fun that way. You end up with,
46.
oh, you did a mixed number? 46.875. Because it was 8s, right? 2.8. You end up with 25 times 15, 15 quarters. What would that be? 375? Anyway, this one ended up being, wait, that was a positive. This one's a negative, right?
Yeah.
So long story short, this one's going to be, I guess, respectively, pretty far down, pretty far up, pretty far down, even farther up. What do you guys think?
That's what we got.
But my window is super zoomed out, true? Do you guys see how let me zoom in a little bit. Do you see how my x's are like -10 to 10? My y's, I definitely scaled that, and I think I'm going by like 10s. 10, 20, 30, 40, 50, 60, something like that. I might even be going by 15s. Oh, 5s? Maybe 5s. I don't know. Question, do you think you could do it?
Yeah.
Ah, you did it, so maybe you can repeat it? There is something called the intermediate value theorem. Don't worry. We're going to miss the concept and the example. That's all we're missing. But I do want you guys until the bell rings. Go ahead and write this down. We're going to talk about the intermediate value theorem at the very end of homework. You're going to write it down in your notes, and when you get to it in homework, look at the example in the book. You guys are honest. Let's see if you're able to kind of figure it out. But I'll go and double check with you on Monday whether you were able to figure out how to do the problem that went with this concept. The idea is, if a continuous function goes from a positive to a negative, it must hit through 0 somewhere in between. Or if a continuous function goes from a negative to a positive, it must hit through 0 in between. This one little theorem has tons of implications in calculus, in physics, in econ. And it's the reason why, if you throw a ball up, we can prove it stops momentarily before it starts coming down. Right?
That's crazy.
See you later. It is crazy. I agree. But it's all proven by this little guy right here. Happy weekend, almost. Hang in there for the rest of Friday. Go rest doing nutrition first, and I'll see you guys when I see you. I'll be here after school for sure for a bit. During lunch, maybe I'll be available. Bye, cool kids.
Very sad.
Like,
Yeah.
Have a good game night, guys.